Hello again. I threatened or promised, whichever word you want to use, to talk a little about Wireshark at the end of my last message to you, video to you. And here's what I've got. I'm going to send you this particular capture. And what I've done is I've looked at stream TCP stream 182. You can just take one of these numbers here and go to it and click on it and then do follow TCP stream. The reason I'm doing this is I want to talk about another protocol in a sense. So I'm going to bring up Word so I can write something. And it'll only take me a minute to get it ready. Now, the idea is we're very security conscious. We're worried about security. So there is another, pardon me, wrong place. Another algorithm, another protocol we can look at. This is called the Transport Layer Security Protocol. So what we're looking at is the Transport Layer Security Protocol. This is called TLS. What happens is the TCP stream uses this. It can actually be used by other higher level protocols also. And if you'll notice, I am relying on one of the usual RFCs to talk about this. This happens to be RFC 8446. So let me write that in. RFC 8446. Let me make sure I wrote that number right. Yes. What this is the two sides, the client and the server, agree on what kind of security they're going to use. They exchange keys. They exchange which method they're going to use. We'll talk about security again later, but just a few comments on security right now. First of all, machine's doing it again to me, sorry. First comment. We have public key cryptography. What that is, it's an incredible method where I can actually tell you how to encrypt a message to me. I can give you the parameters to take your message and encrypt it. And yet, according to the best mathematical concept we know, we can't, the person who is getting my public key cannot undo messages that that have been sent with it. This the algorithm we're looking at is called the RSA algorithm. It's named after the three people who discovered it believe it was at MIT. It is based on the difficulty of prime factorization. I.e., given a large number, it is difficult to find primes that multiply together to get this number. This is an assumption that we have made. Nobody has proven that this is an NP problem. Nobody has proven that there isn't some reasonable polynomial time algorithm to do it. Most people think there isn't. The problem is, as computers get better and faster and faster, the brute force methods, you've seen some of those in programs in some of the earlier courses on finding out if a number is prime, for example. They work better and better, and it's possible for people to find the factorization. But the object is it doesn't scale up. So we keep producing larger and larger numbers. The way this works is the person who wants to have a public key finds two very large primes. We may be talking 500-digit primes, 1,000-digit primes, and then multiplies them together and uses that and some theorems from mathematics to find the key, what he or she needs to send, so people can send them secret messages. Now again, the RSA algorithm is used. Sometimes people use it only to send the key that they want to use some other algorithm, like the Diffie-Hellman algorithm. So they don't want to put too much in it. They want to use it for special cases. You've got to understand that I think more than $1 trillion goes across the Atlantic on the internet each day. So you got to have pretty good protection for when you're talking about transactions that could result in a few $1 billion losses. Now, that's where we are. But a newer method of cryptography, CRYPT, is based on elliptic curves. Only the people who really like mathematics will probably understand this one. These are curves. I've got an example of them out here somewhere. I guess I have to re-get it. It'll only take me a minute. Now I'll get the Wolfram. There are some elliptic curves. They're all in the form y squared equals x cubed plus ax plus b. pardon me. No, yeah, here it is. Y squared equals x cubed plus ax plus b. Now, once they get those, they do a transformation using, I think they would call it secants that go through it. And there's a whole theory of how this is done. Using these curves, they then can create a particular code. So the curves are of the form, again, y squared equals x cubed plus ax plus b. That is, I guess, one of the frontiers in cryptography. It's used, and hopefully it will survive the quantum computing attacks. It's probable that the RSA will not, unless you get unbelievably huge primes. So that's the idea is we need to have some kind of security for what we're doing. So how do we decide what we want to use for security? The TLS is a method for the client and the server to agree on what code to use. That's all it really is. If you look at this here, we go back to the RFC. It's a big RFC, by the way. But in the introduction section right here, the primary goal is is this, and there are two primary components. I'll copy that over here so you don't have to go to read it over there. And the best part is we can see most of this by using Wireshark. So let me go up to the top of this and say from RFC 8446. So I looked at this, and further down in here, it shows the handshake. You remember the handshake in TCP. Well, here's another handshake. And we can look at this part right here, and we can see if we can find some of that in our Wireshark. Oh, I put it in the wrong place, pardon me. Gotta go down further. So down here, the TLS handshake. Now let's see. The first thing we're supposed to look for is a client hello. So I've got a capture here, and if you look, there's the client hello. By the way, above that we have the TCP handshake. Now we're doing the TLS handshake. So the client hello, see what we have. Here's the transport layer security. What is it? It's a client hello. It says it's generating a random number for us to be used in taking care of some things. It tells us what kinds of items we can use. This section here, I actually asked you about this in the last Wireshark homework. What this is a list of possible codes that can be used. And there's all kinds of other comments on this. After the client hello, according to the TLS, we have a server hello. So let's go back to our Wireshark. There's the server hello. So it comes back to us. And then after the server hello, we're supposed to have a certificate that goes the other way. And I think we do. If you look right here, there it is. And then we finally have the exchange, the server key. It doesn't show it here, but that's the last part. Maybe I didn't copy enough. Let me check. I think I didn't copy enough. No, looks like I did. So this is the way that TCP ensures security. It doesn't rely on itself. It relies on another protocol, which has been defined to allow the setting up of how the two sides want to encode everything. 8446 means that this is a relatively young RFC. I don't know if I can quickly see the date on it. It's pardon me, I gotta move this a little, or I can't see the date. August of 2018. So it's only about 2 years old. There were previous versions. This is actually version 1.3. So that explains, I hope, gives you some idea of about the TLS that you see here. TCP is using it. Other protocols could also use it if they wanted to. I don't know if any actually do in what I've got here. I might check that out later. So that's what I want to say. I'm going to send you this video, that little sheet that I've been typing, and I'm going to send you this capture so you'll be able to look at it yourself. So long now.